Thanks for stopping by the channel today. My name's Jason. I'm KC5HWB. This is the extra class. This is the final class in the 3 classes of amateur radio licensing that exist in the United States today. Some of my most popular videos on this channel have been the technician class and the general class, which is class 1 and class 2, or level 1 and level 2, if you will. This is level 3. This is the final level. This is the top license you can get. And I want to thank the North Richland Hills Amateur Radio Club for allowing me to record this Zoom class they did at the end of 2020, beginning of 2021. It was about 8 6 to 7 hour sessions, so you're in for a wild ride today. Go through them as many times as you want to. Fast forward, stop, pause, rewind, whatever you want to do. Play them over and over again. This is good information for those of you who are currently a general and wanting to upgrade to amateur extra. Thank you to the North Richland Hills Amateur Radio Club. Their website will be linked in the description of the video below, and I hope you enjoy the video series.
Let's get going. We're on antennas section. Starts on page 213 if you're following along in the book. The study sheets, figures are all embedded in the question list on this section. So we will not go over the study sheets separately. There's 3 of them that I ended up needing to make all the figures. And we'll just get right into it. Let me share the questions for antennas. We'll get started. Page 213. Radiation resistance of an antenna. An antenna model, electrical model for an antenna, consists of the loss in a feed line, commonly coax. It can be ladder line as a different type of feed line. You have a radiated power, which is the radiation resistance, which is what power the antenna actually transmits and turns into electromagnetic waves. And you have a ground resistance, which can include loss resistance in the antenna itself, such as poor connections in a Yagi antenna, so that the elements of the Yagi have resistance in series with them. So when currents flow, you lose power. That's a loss. That's part of the antenna loss resistance. And if it's a vertical antenna, where only half of the dipole is present, you have a ground resistance that has to be accounted for. So in antenna loss, both types of loss are added together, antenna loss plus ground loss. So to figure the efficiency of an antenna, you would take the radiation resistance, which is useful radiated power, divided by the sum of radiation resistance and all the losses in the antenna system itself, including antenna loss and ground resistance loss, if there's any present. Now, dipole antennas wouldn't have a ground resistance loss, but they would have antenna loss resistance in the wire, which is usually why a large diameter wire, large gauge wire, is good for dipoles. Some people use small gauge wire, very thin wire, for dipoles for one reason: you can hide them easier. They're harder to see for those people that have to hide antennas. Second, that might be all the wire you have. It's okay to use a 22 gauge wire for antennas. They work. They just have a little bit higher loss than if you had used 12 gauge wire. So that's part of the antenna loss. So what is the radiation resistance of an antenna? We'll start with that part of the question.
Hey, John.
Hello? Hello?
John?
Hello?
I have a question.
Yes.
Do the radios count as part of the ground loss?
Yes, they do.
Okay, on a vertical?
Yes. One reason you use radials is to reduce the ground resistance. And the more radials you use, the lower the ground resistance will be. But of course, you know, with everything, there's a point of diminishing returns. If you get more than 15 or 20 radials, you're not going to help it if you go to 50. That's, you know, 15 or 20 is a common number of radials that can be used. If you have 3 radials, it'll be way better to have 9 or 10 or 12. And yes, the radial resistance and the connection to actual conducting earth does increase and count against your ground loss. Now, I think there's a question about ground loss. So that's coming up.
Thanks.
All right. Does that answer your question?
Yes, thanks, John.
Okay, you're welcome. Yeah, if anybody's got questions, just ask a question and we'll take care of it. It'll be better to answer the question right when we're dealing with that part of the test question and take care of it so everybody can understand and benefit from the explanation. And if you're wondering about understanding a question, there's probably another 2 or 3 people that are too. So it's useful to go ahead and ask the question right then. I will attempt to take a breath once in a while so that you can get a question in instead of just talking nonstop. Eventually, I guess I'll get tired of talking sometime. Hopefully that point will come after 4:30. You remember that we agreed to have a question and answer period after the 4 o'clock stop time for the presentation of the sections, and I still plan to do that. If Hugh wants to stick around for that, you're welcome, Hugh. You're not obligated to do that. I can take questions to the extent of my knowledge and experience. Otherwise, if I don't know the answer, we'll jot it down and research it and get you some answers in a later email. But let's deal with this one right now. This is the radiation resistance of an antenna. That is the value of a resistance that would dissipate the same amount of power as what is radiated. That is the actual useful power that's radiated from the antenna. It's called the radiation resistance. Now, it's not a real resistance. It's the power that the antenna radiates and turns into electromagnetic waves. That's the only useful power. Any power that's dissipated in resistance or loss or ground loss or loss in the elements of an antenna, in the case of a Yagi, or the 2 elements of a dipole. You got 2 quarter wave elements in a dipole, is just lost to heat and it's just gone. So that's the model we talked about. What's included in the total resistance of an antenna system? Well, you would have the radiation resistance plus loss resistance. That's the total resistance. And in typical engineer calculation, you would use that as the total resistance for efficiency, divide that into the useful power that the antenna radiates to get efficiency. I don't think efficiency is a question, but that's what it means. What factors affect the feed point and impedance of an antenna? Every antenna has a feed point impedance. Which factors affect that? Transmission line from the transmitter doesn't. Antenna height will. The antenna tuner at the transmitter is not changing the antenna feed point. Input power level doesn't, unless it's in a bad way, like you have a balun that's overheating. But that's bad because that overheating is loss. You don't want that. The answer is antenna height. Antenna height is the greatest factor that affects the feed point impedance of an antenna. Really, you want the antenna as high as you can get it for that reason and others. What is antenna efficiency? Oh, here, it does have an efficiency question. I forgot about that. Sorry. It's radiation resistance divided by total resistance. What's the total resistance? Radiation resistance plus loss resistance. What's given up in power dissipation? That's bad. You want antenna efficiency high so that most of your power goes off into electromagnetic waves, because the receiver at the other end is only hearing the electromagnetic waves. It can't get any use from the power you dissipate in your antenna as heat. Which of the following improves the efficiency of a ground-mounted quarter wave vertical? Radial system will improve the efficiency. Isolating the coax shield from ground, no, that doesn't help. Shortening the radiating element, that doesn't do efficiency, that just mistunes the antenna. So it's not all the choices, it's got to be installing the radial system. And yes, the radial system does wonders for the efficiency of the ground-mounted quarter wave. Which of the following factors determines ground losses for a ground-mounted vertical antenna in HF? This is HF range. So what factors determine the ground losses? Soil conductivity or low.
Question.
Okay, question.
I have a buddy stick with a coil on the bottom, you know, mounted on a tripod. The tripod is not, you know, metally connected. It's just sitting up there, and I never ground my antenna at all. So if I want to ground it, do I need to just hook it onto the bottom of the antenna up top and run it to the ground?
John, you want me to answer this since I have one of them?
Yes, go for it, Hugh.
Okay, so on the buddy pole system, if you make a vertical antenna out of it, on the red pin that you connected to the antenna itself, then you have a black pin that is supposed to go to a counterpoise. And a counterpoise for those kind of antennas, you usually get it with it. It's a big long wire that you make a quarter wavelength out of it and then stake it to the ground, physically to the ground. And it shouldn't touch the ground all the way out to where it's staked.
So the ground does not go to the main vertical. Mine's just a buddy stick, you know.
It goes to the shield side on your coax.
Well, there's only one connection on the coil, and of course that goes to the. Oh, I see what you're saying now.
You should have it.
Tell me one more time where I hook the ground. Okay.
So when you come out to your antenna with coax, the center conductor goes to the vertical antenna, and the shield on the coax goes to the counterpoise.
Right.
Let me get your. I'll post a link here in a minute on the chat, and all of y'all can go out there and look. There's a book out there that shows all the different ways you can use a buddy pole, and then we can get on with the class.
All right. Thank you.
All right, thanks, Hugh.
Oh, listen, I need your email address so I can email you a request for those diagrams you can PDF while ago.
They're in the chat.
From the downloads?
Yeah, is your email address on there somewhere?
Yeah, it's K5GD Golf Delta at ARRL.net.
My hearing is not great, so just don't worry about that, okay?
Hugh, will you put my email address in the chat window?
Yes, I think so.
Kilo 5 Golf Delta at ARRL.net.
Oh, I think I saw that. I did see that somewhere. I'll look for it in a minute.
Yeah, that was on the introductory screen or information share that I had up during lunch and before class.
So,
Kilo 5 Golf Delta.
so what you were telling me a while ago was I hook the ground to the counterpoise connect on one end or the other, right?
Yes, sir. I'll send diagrams so you can see how it all goes together.
Thank you, sir.
And we can include that link in the class notes that we'll send out later for today's session. And yes, Hugh can post my email address, Kilo 5 Golf Delta at ARRL.net.
Wait just a minute. I'm gonna get something to write with. Okay.
All right. And you can send me an email.
Okay, I'm ready.
Kilo 5 Golf Delta.
Kilo 5 dot what?
Kilo 5 Golf Delta.
Oh, golf. Delta, got it?
At ARRL.net. Alpha Romeo Romeo Lima.
K5GD at ARRL.net, right?
Yes, that's it.
Okay, the check's in the mail.
All right, send it on and we'll get that to you. Thanks for asking the question. I don't have a buddy poll, so I wouldn't have known the answer. Thanks, Hugh.
You're welcome.
Okay, we got that one done. How is the far field elevation pattern of a vertically polarized antenna affected by being mounted over seawater versus soil? Seawater is salty and it's a very good conductor. It's almost like a sheet of aluminum. It's such a good conductor and reflector. So soil is not near that good of a conductor. So that's going to be a very good ground plane, and the low angle radiation increases for a vertically polarized antenna. Vertically polarized antennas like a quarter wave vertical or a buddy pole sitting vertical is a vertically polarized antenna. Use it over seawater, put one up on the beach. Even fresh water works good, but certainly seawater works better than dirt, especially if you're rocky soil like West Texas is more rocks and sand. There's not much conductivity in that soil. Put it over seawater and antenna works way better. And the low angle radiation increases, meaning we'll get into the low angle radiation a little bit. Which of the following conductors is best for minimizing losses in an RF ground system? We're looking to minimize loss for RF. You want to use the wide flat copper strap. You can also get woven wire that's wide, like an inch or inch and a half wide. It's really expensive. Copper strap you can make out of copper flashing that you find at home improvement stores, Home Depot or Lowe's, such as those. But if you get that wide flat copper strap, that's the best way to build a low loss RF ground system. Now, most people would use wire, stranded or solid wire, for radials for a vertical antenna. That's good. If you made it out of flat copper strap, that's even better. So that would minimize the loss.
Is this what you would be connecting off the back of your radio then for a common tie together for grounding, or is this different?
Yes. Yes, this is a good way to connect the radios in your station inside your ham shack to a wide copper strap or the biggest wire you can find to run outside. So I've got a 6-gauge copper wire that runs around the perimeter of my ham shack, and it goes through the wall to the ground stakes outside. And I tie everything to that. And that's my station, RF station ground. It's not wide flat copper strap, but the wide flat copper strap would minimize the losses. 6-gauge copper wire still has some loss at RF. But I had the wire, so that's what I used. Which of the following would provide the best RF ground for your station? We're looking for the best RF ground. Which of these choices sounds like the best RF ground? The best one is the electrically short connection to 3 or 4 interconnected ground rods, driven right straight into the ground. And where I've got my ground rods sitting, I think I've got 3 that I've got the 6-gauge wire connecting to, and then the wire coming through the wall connects to the middle one. And they're all driven into the ground in the flower bed, and that flower bed stays wet. So that's a real good low impedance connection for RF. Metal water pipes wander around through your house. They're good if that's all you have, but it's better to have the ground rods driven right straight to the earth with a short connection. What's the primary function of an external earth connection or ground rod? What would be a primary function for those ground rods? To take care of lightning. Now, I hope you don't get lightning inside your ham shack, because that's just wild electricity, tens of thousands of amps floating around looking for a low impedance to go into. And it does it in less than a microsecond. That's the job I'm working at right now, is dealing with how to protect electronic equipment from lightning strikes. And routinely we test at 5,000 and 6,000 amps. Those are kind of like baby lightning strikes. And it all happens in a 1/10 of a microsecond. It doesn't take long for that much current to find a place to go. It will find the lowest impedance to earth ground that it can. So the primary function of an earth connection and ground rod is for lightning protection. And they're very, very necessary. What's the radiation pattern of 2 quarter-wave verticals spaced a 1/2 wave apart and fed 180 degrees out of phase? What does all that mean? Next picture, and this is from your book. The explanation at the bottom of the page is just extra stuff I stuck in there, and that would be useful information to go with this. The Greek letter lambda, that's that kind of swirly thing with an extra foot, is commonly used as an abbreviation for wavelength. So any of these pictures you see, lambda, the Greek letter, that's wavelength. And as a reminder, wavelength is the speed of light divided by frequency. So I think that will come up next week in transmission lines. So you need to know that for transmission lines, antennas, and to figure out the free space wavelength of any RF signal. It's all right there. Wavelength is the speed of light divided by frequency. Okay, back to the question. What's the radiation pattern? 2 quarter-wave vertical antennas, a 1/2 wave apart, fed 180 degrees out of phase. Well, I didn't make the feed phasing on these diagrams, but this first one on the left, there's 2 quarter-wave verticals. We're looking down from the top on these diagrams. So number 1 and number 2 dots are the quarter-wave verticals sticking out at you from the screen. They're spaced a 1/2 wave apart. And if we feed them 180 degrees out of phase, you get a figure 8 and antenna pattern oriented along the axis of the array. The axis of the array is the line that joins the two verticals. And so coming out of that is a figure 8 pattern where there's nulls off to the side, perpendicular to the line between the two quarter wave verticals. And the most radiation will be off the ends, looking out from the ends of that 2-element array. This forms a 2-element array. So the answer to this is the figure 8 oriented along the axis of the array. This is for fed 180 degrees out of phase. No, it's not cardioid. That's not the right answer. My mouse is not cooperating. It doesn't like my desktop. It wants to be on a piece of paper. Sorry. Okay. So we got these antenna patterns right here are quarter wave verticals, and they're spaced at different spacings and fed differently. So the first one is fed 180 degrees out of phase. And so we get this antenna pattern where the power is radiated out along the ends of the axis between the antennas. The next question is, quarter wave verticals are quarter wave apart and fed 90 degrees out of phase. Quarter wave apart, and if you feed these at 90 degrees out of phase, same two quarter wave verticals, and they're moved halfway in to a quarter wave apart, and you feed it 9 degrees out of phase, you get this cardioid. The cardioid curve is this one that has a very deep null right here in the center off the end of the array. Otherwise, it's a broadly rounded, almost omnidirectional pattern, except for the null. And we'll use that null in radio direction finding. So we have two quarter wave verticals, a quarter wavelength apart, fed 90 degrees out of phase, and you get the cardioid pattern. And that's useful sometimes to have one like that. So if you have an interfering station that's off over here, you call that west, up north would be up. So west of you is a big interfering station, like we used to have high-powered foreign broadcast AM stations right in the middle of 40 meter band. You would point that null of the cardioid over here toward that station and really reduce his power that's coming into your receiver. The third question is, what's the radiation pattern of the two quarter wave vertical antennas, half wave apart and fed in phase? If you feed them in phase, you get the figure 8 broadside to the axis of the array. That is this choice. See, here's the same two quarter wave verticals, number 1 and number 2, as we had the first time. Only this time, instead, these two were fed 180 degrees out of phase. So directly out of phase, you feeding the two verticals, you get the pattern off the ends, but if you feed them in phase, you get the pattern off the broadside. That's how you can have a fixed quarter wave vertical array and switch their pattern by changing the phasing of how you feed them.
What is the polarization of these?
They're all vertical.
They're all vertical?
Yes, they're quarter wave vertical antennas tuned to the same frequency.
Hey, John, that's not the same picture that we have in the book.
I rotated it.
You rotated it.
In the book, the two vertical antennas are on top or vertical from each other, oriented up and down on the page. I rotated it so that the antennas are the same as 1 and 2 when you feed them out of phase. So I wanted to show that the same vertical antennas at the same position, if you change to feeding in phase, it switches the pattern to broadside instead of off the end. I mean, I read that going like, well, that's confusing because the pattern looked the same, but in the book, it just shows the antennas, one up here where lambda over 2 is, and the other one down here in the middle of the other circle of the pattern. So here I wanted to look at how you can have the antennas at the same physical position and just change the feeding of it, change the phasing of the feed, and you switch from linear off the ends of the array to broadside to the array. So that if you have a lot of area and can put up some quarter wave verticals like this, you can switch from an east-west oriented radiation pattern to a north-south oriented radiation pattern. But it's the same
Question?
effect as what's in the book.
But is that going to be the same diagram that's in the book as what you have here, or is it going to be what Gordo has in the book on page 217?
I don't believe with this question you get the patterns, because these patterns are not part of the
The patterns are in the book.
the patterns are in the book. They're for illustration. The patterns have to look like the diagrams that come with the question are part of the question pool diagrams. And that's the link that I sent in the chat to the volunteer examiner coordinating committee and their questions and diagrams. Because if you go to that link for the VEC coordinators, that's where you can get all the questions and all the elements and the diagrams. Look on page 230 and 231. We'll get to those in a minute. Those are antenna patterns, one azimuth, one elevation. Where it says figure E91 and E92, those are figures that will come with the questions. Now these on page 217 will not. They're for illustration only and will not come with the question. So you kind of have to remember when you talk about, if you get a question that talks about 2 quarter wave verticals, you feed them out of phase, you get the figure 8 oriented along the axis. If you feed them in phase, it's going to be broadside. And if the quarter wave verticals are a quarter wave apart and fed 90 degrees out of phase, you get the cardioid. You're not going to have the pictures. You can remember the pictures. Another thing about taking the test, you can have a blank piece of paper. So if you want to, jot notes or make calculations or jot down some diagrams to remember this stuff, you can remember how the antenna patterns are put together and draw them for yourself. You just can't take it with you into the test. But you can sit there with a blank piece of paper. They'll give you a blank piece of paper. And I suppose if you do it virtually, you'll have to show the piece of paper that it's blank before the camera so they can set you up with a valid test session and show them you got a blank piece of paper, and you can then sit there and draw these arrangements out and remember how to feed them, and then you get the answer right.
John?
Yes.
Okay, for the exam, there are a scope screen, the FETs, the diodes, some logic, then there's a couple of amp circuits, and then the rest of them are all graphs of antenna patterns that come from Smith charts. And that's
Yes.
all that you will get for your test. All the rest of these pictures in the book aren't on the test.
Yes. You can download the pictures that will come with the test from the VEC question pool link. And we'll put that in the email we'll send out from today's class, along with 2 or 3 other things, the buddy poll link and whatever else we come up with. I'm taking some notes, and I hope you is too, in case I miss something, but that's what I've got in my notes.
I mean, I can scan them in, put them on the thing right now.
Hey, I got a question on these
Okay.
patterns.
Back to the patterns?
Yeah.
Okay.
Now, yeah. 2 questions. Like, now these are like top-down views of the radiation pattern off the ends of the antennas, correct? So
Yes.
then this if these are vertical, then that radiation pattern would be perpendicular to it, or parallel.
The radiation pattern will be out along the surface of the Earth.
It'd be like
Okay,
a
okay.
bird. It'd be like a bird's eye view of it.
Right.
Yes.
Then okay, I understand. The second question: how do you change the phasing? I mean, or is that beyond the scope of this? I mean, how do you alter the phasing so that you get these different patterns?
The answer is by length of feed line. And we'll cover that next week in the transmission line class.
Okay. All right. Yeah,
But it's by length of feed line. Yes.
Okay. Yeah, this is one of the areas I didn't understand. Was waiting for. Okay. But thank you. Yeah.
But I mean, the short answer is by length of feed line. Obviously, that's going to be tuned to a frequency. Well, okay, so are the quarter wave verticals tuned to a specific frequency. So this is going to be like an antenna system for one band of operation. Yeah, I mean, you can obviously use relays, electromechanical relays, to change different feed lines and different lengths of coax. And if you get an antenna book, ARRL antenna book, or I've even seen it in the radio amateur handbook from ARRL, or just search online for how to feed vertical antenna array. You'll see arrangements of relays and coils of coax that form phasing lines. They're called phasing lines, is what I've seen them called, and get some ideas how to do that. That's always something I've wanted to do. I just didn't have enough room in the yard or a big pasture to do it in.
I was thinking vertical's got a very small yard. I mean, California. So I was like, well, maybe I go vertically, and if this is a pattern I can obtain, maybe that's an alternative to a long wire. But thank you. Appreciate it, all those hints.
Okay, you're welcome. Any other questions? All right, then let's move on. We did those. Okay. What happens to the radiation pattern of an unterminated long wire antenna as the wire gets longer? Well, I've made a sketch down here of a long wire. One type of a long wire antenna is called a beverage antenna. That's 1 or more wavelengths long. This question's talking about antennas that are 3 or more wavelengths long. And what happens is, this is an attempt, this stuff at the end on the right was an attempt, but fell apart quickly, of showing the azimuth antenna pattern. So as the length is increased, this main lobe that shoots off the end of the antenna gets bigger and bigger, and these side lobes will be reduced. These are called side lobes. This is the main lobe that comes off the end of the antenna. And this is radio energy, electromagnetic waves propagating along the ground, obviously in a straight line. So until the earth curves, they're along the ground, but then eventually they'll get up to the ionosphere, as we talked about in the first week, the ionospheric propagation. See, all this stuff ties together. It's not just single topics, so it all ties together. That's what's fun about radio. I like tying all the pieces together. So this is an azimuth radiation pattern looking down from the top. We'll go over these some more if you don't quite grasp it yet, but we'll go over it a bunch. And the radiation pattern of this long wire, the longer the wire, the more the main lobe aligns with the direction of the wire, is what this question's getting at. So if you're going to put up a long wire antenna, plan on minimum 2 or 3 wavelengths long. 4 or 5 is even better. And the radiation pattern shoots off the end, the unterminated end. Now, obviously the feed is over here at the other end of the wire. And if you have enough coax and have some relays, you can put some relays at each end and feed one end or the other and reverse the direction of which this main lobe is going to take off. So that might be useful if you've got 2 directions right opposite each other. You can change it that way. I mean, relays at antennas are good to use. Just don't change the relay while you're transmitting RF power, because that'll burn the contacts. I've seen that happen. Anyway, unterminated long wire, the longer the better, and the lobes go off the end of the unterminated end of it. So what's a folded dipole? A folded dipole looks like this at the bottom. It's a dipole, that's the bottom pair of lines. The total length is a half wavelength, but there's another wire in parallel with it. And this can be made out of ladder line, like the feed line coming off of it here is a ladder line. And ladder line is very useful. If you wanted to take it to a coax, you'll need a balun for it to work right. Otherwise, the impedance and the antenna pattern is going to be messed up by putting the ground of the coax to one wire and the center coax to the other. You need a balun to make this work right. But a folded dipole is where you put another wire in parallel with the 2 quarter wave dipole wires, connect them at the end, and the longer wires connected here across the feed point, and it works just great. I've built several of these for various frequencies. One field day, I built one for 10 meters, and we got out like gangbusters on 10 meters with this folded dipole. And some other details to it, but that's covered in transmission lines. You can make I used to make these back in the NTSC television days as TV antennas, because the feed point impedance here is 300 ohms, which is what a TV flat wire and lead-in wire needs, is 300 ohms. And so the feed point impedance of the folded dipole is 300 ohms. And if you cut this length, the total length, at a half wavelength at the lowest frequency, which in our area was like 60 megahertz, it'll pick up to 3 or 4 times that wavelength and be good for FM radio and TV stations just from this one antenna. But it has to be cut at a half wavelength at the lowest frequency. All right, so what's the question? What's the folded dipole antenna? Well, we just saw it. What is it? It's a half wave dipole with an additional wire, parallel wire, connecting its 2 ends. And it connects the 2 ends just right straight across it in parallel with it. Use a piece of ladder line for this. That's great. It works great. I've built them. Folded dipole. What's the approximate feed point impedance of a folded dipole antenna? Well, I just said 300 ohms. Like the antenna impedance for TV antennas and their flat line transmission line. Ladder line is another type of transmission line. We'll talk more about that next week with transmission lines. Which of the following is an OCFD, off-center fed dipole? Is what that means. That's an acronym for off-center fed dipole. Here's a sketch of an off-center fed dipole. It's a dipole consisting of 2 quarter wave segments joined in the middle. So the total length is a half wave length, and it's fed at a third of the way down one leg. And I kind of messed this explanation up because I put 12 to 18% of the total half wave length. Well, if you figure that on a quarter wave length, that's about a third, 33%. And I think that's the answer to the question. It's a dipole fed a third of the way from one end with the 4-to-1 balun, and it gives you multi-band operation. So the dipole is fed a third of the way from one end, from one of the quarter wave dipole ends. And there's lots of different commercial antennas made in this way called OCFD antennas. And they all kind of change the feed point. Some of them have a length of ladder line before the balun, and we'll talk next week in transmission lines about how impedance changes along transmission lines. So you use this as a matching stub. Transmission lines can be used as matching stubs. That's for next week. You'll have to come back next week and hear how all that works. That's interesting stuff. Now, also in this picture is a G5RV. This is a dipole with a stub of a specific length, which I suppose the designer of the G5RV picked so that this is a multiband antenna. Run the stub to a balun and then to a coax, it goes to your radio. And let's see what the question is.
Hey, John.
Hello.
That piece of ladder line is approximately a quarter wavelength.
The selected length is a quarter wave?
Approximately a quarter wave for the G5RV.
Okay. A quarter wave at what frequency?
The center frequency of the G5RV, and I think that's 20 meters.
Okay. So it would still be a multi-band antenna, and that would make it work best on 20 meters, which is a good band to have a good antenna on. So you're saying that you use a quarter wavelength for this length of the stub and ladder line?
It's approximately, yes.
Approximately, yeah. Okay, so it's not real critical then. And so that will match it for multiple bands.
How long's the overall length then? Or is that band dependent?
I'd use a half wave on 20 meters.
Oh, it's a half wave.
I haven't built one of these. I don't know.
Okay.
You got any information about how long it is?
I'll
have to dig it out and measure it. I can find out before next week.
Well, I mean, is it a half wave, a quarter wave? I mean, obviously by frequency is going to vary.
They're quarter wave elements on each side.
Quarter wave on each, okay.
And if I remember right,
Overall,
they are cut for 20 meter also, and then it'll work on 40 all the way down. They do make one that'll work on 80, but it's huge. I mean, that thing is a beast.
Yeah, I've read about them. I wanted to get up a antenna that I can work on 80 meters and be good on 40. And I look at these and they're like 160 feet long. I'm going like, no, my lot's not near that long.
Yep.
I'd have to bend both ends in half and then it might fit.
Yeah, it looked like a zigzag in my yard.
Yeah. So, yeah, it would have to be a zigzag, all right, and fold it back on itself. Might defeat the whole purpose of getting that type of wire antenna.
Well, that's funny you mentioned that, because that was a question that was asked on one of the nets yesterday that Gordo replied to, of how to,
Oh,
like,
yeah.
on a small lot run something. You have, and it was more for the ground radials, and you can run a zigzag pattern for them. But as long as you don't cross, the radial, like say if you have a 40, you don't cross it across the 20. They're separate, but a zigzag pattern can fill a small lot. And the same thing, with the antenna itself. But you lose radiation, propagation pattern off the way the pattern coming off the radio, the primary is.
Yep, just get a wire up and get it tuned and off you go. That's what I mean by saying any radio doesn't work without an antenna.
Hey,
I
John,
found that out years ago.
you're off center fed dipole. That's a mistake there, right? On your balun there, there's supposed to be a gap there where your 4-to-1 balun connects to.
Oh, you mean where I got the wire looks like it's joined?
Yeah.
Compared to the G5RV? Yes, yes, you're correct.
Okay,
Very good.
Just wanted to make sure.
Yes, thank you. Yes, you're correct. No, if you short out the ladder line going up there, it's not going to do anything.
That's what I thought. Just wanted to make sure for my own for my own peace of mind.
Yeah, sorry, I messed up that drawing.
No worries. I'm not trying to punch you out or anything. Just wanted to make sure.
Well, that's all right. I realize now it's a mistake. It was late when I was doing these, so there could be other errors. So you gotta be alert. You might catch something else. You never know. Anyway, I'm not an expert and I'm not a perfect artist either. So you've already seen that. Okay, so which answer describes the G5RV? Let's go with the multiband dipole fed with coax and a balun through a quarter wave open wire transmission line. Open wire transmission line is another name for ladder line. So that's a G5RV. Which of the following describes a ZEP antenna? Next page shows the ZEP antenna. ZEP antenna is a ladder line that one side's not terminated at the top. The other side feeds a half-wave wire. So the half-wave wire has the highest impedance out here at the ends of it. Each end is a very high impedance. So you would use a quarter wave transmission line, and the properties of transmission lines is in a quarter wave, the impedance is going to be inverted from a high impedance at the antenna end to a low impedance here, where you can connect it straight to a radio or a balun and then a coax. And so the other end from a high impedance quarter wave transmission line is a low impedance. Connect that. You might want a antenna tuner for the coax coming in, or you can connect the ladder line straight to the antenna tuner. And that's a ZEP antenna. Extended double ZEP is very interesting. It's got two pieces of 5/8 wavelength wire on each side. It's for a total of 1 1/4 wavelength long, which gets long for the HF bands. And you're going to need some matching inductance or a stub. You can use stubs. Stubs become matching impedance elements, and we'll see that next week in the transmission line section. But you'll need some matching inductance. Now, if you've ever had a 5/8 wave vertical, that's half of this extended double ZEP. So the extended double ZEP is 2 5/8 antennas with the matching inductance, and a 5/8 wave vertical has a matching inductance at the base of it to go to a 50 ohm coax. So it's the same antenna. It's just extended double ZEP. You got two of them. So that would be a 5/8 wave total 1 1/4 wavelength. Okay, so how do you describe a ZEP antenna? That is an end-fed dipole. Doesn't have anything to do with satellites. It's not a vertical array. It's not zip cord. It's an in-fed dipole. And I didn't highlight ZEP right here. ZEP is an in-fed dipole, just like this. You have a dipole, half wave. Dipole implies half wavelength long. Feed it at the high impedance point with a quarter wave transformer transmission line section to get to a low impedance, and off you go. Extended double ZEP is described as a center fed 1 1/4 wavelength antenna. That's all it is. Then you need some matching components to make it match down to 50 ohms. Okay, now, very interesting topic, isotropic antennas. An isotropic antenna is not a real antenna, contrary to some people's beliefs. It is a theoretical omnidirectional antenna that radiates equally in all directions around it. Up, down, sideways, north, south, east, west, into the air, into the earth. Doesn't exist. It's used as a reference for antenna gain. It's what antenna engineers commonly reference antenna gains to for antennas they're designing. Isotropic antenna is a theoretical omnidirectional reference for antenna gain. And I think this is on page 220. That's my 220 note over here is what that means. Now, a half-wave dipole has 2.15 dBi gain. What that means is that you've kind of squished the equal radiation, equal electromagnetic radiation around this point source. Sometimes this is called a point source because it doesn't have any length. It's a point that radiates electromagnetic energy in every direction around it from itself. So going outward from itself, it's a unity gain pattern in any direction you go. It's a reference for antenna gain, and the half-wave dipole has 2.15 dB gain over the isotropic. Now you need to remember this number. Antenna engineers quote that in their sleep. They dream all night. 2.15 dBi is a dipole. So you have to remember that number. We'll use it again. Let's see. All right, we defined isotropic. Let's talk about ERP, effective radiated power. Some rules and regulations from the FCC talk about ERP, effective radiated power. What comes out your antenna? So what comes out your antenna starts out as your transmitter power, and you have to convert that to dB, which is, well, we're not going to do that calculation. You don't need a calculator. We're going to do all this without a calculator. So ERP, effective radiated power, you add the antenna gain, subtract the losses in your antenna system. Losses in the antenna system can be feed line loss, antenna loss. If you're operating a repeater site, you may have filters. You'll have a duplexer, so you subtract off the duplexer loss. And for ERP, you have to know what's the reference. Is it a dipole antenna reference or is it an isotropic reference? ERP will be given as dBd or dBi, depending on which reference it is. dBi for the isotropic, dBd for the dipole reference. Now let's review decibels for a minute. I'm sure everybody lives and dreams of decibels and logarithmic tables, right? Right. 0 dB is unity gain. Isotropic antenna has 0 dB gain. That's the reference. It's a unity gain equally in every direction. If you go 10 dB in power, that's a factor of 10. So 10 dB transmitter output is 10 watts. 20 dB transmitter output is 100 watts. So 30 dB transmitter output would be 1,000 watts, on like that. If you want 200 watts transmitter output, add 3 dB to 20. So 23 dB is 200 watts, because the extra 3 dB over the 10, over the 20 for 100 watts is a factor of 2 in power. 6 dB is a factor of 4 in power. So 400 watts would become 26 dB. See how easy decibels are? They're easy. Okay, now what are we going to do with all that? The question is, what is the effective radiated power relative to a dipole of a repeater with 150 watts transmitter power and some losses? 2 dB feed line loss, 2.2 dB duplexer loss. Those are the losses. And the antenna gain, no, what did I do? I did something wrong. The antenna gain is 7 dB relative to a dipole. See, they give you the antenna gain relative to a dipole. So it wants to know what's the effective radiated power relative to a dipole with these parameters. So here's the calculation. You take antenna gain plus 7 dB, subtract off the losses. Our losses were 2 and 2.2, total of 4.2. So the net antenna gain minus the losses is 2.8 dB. The antenna takes the transmitter output power, adds 2.8 dB of gain. Now 2.8 is almost 3. So if it was a 3 dB gain, 150 watt transmitter would be an ERP of 300 watts, but it's not quite 300. So, or it's not quite 3 dB gain, it's 2.8. So it's a little bit less than 300. So the answer you pick is 286 watts. See how easy that is? You don't need a calculator.
Okay, rewind on that one.
That's the usefulness of rewind. You'll have to watch the movie to hit rewind.
No, I got the up to the approximately 3 dB.
Right. Okay. So approximately 3 dB. If it was a 3 dB gain, that's doubling the power of the transmitter. So that would be 300 watts. But it's not quite 3 dB.
That's what I missed. Doubling. Okay.
300. I mean, yeah, you can find an exact multiplier for 2.8 dB with a calculator, but you don't need to, because it's not 400. It's not going to more than double the power. It's not going to be 78 watts. That's roughly half the power of the 150. It's not 2 kilowatts. It's not going to do that. The answer is 286 watts, just below.
No, I missed the 3 dB is almost 2x. So
okay,
I missed that.
Well, that's this whole thing here in the middle. If it was 3 dB of gain, it would be a ×2 of the transmitter power. But it's not. It's not quite 3, so it's not quite 300, so it's 286. Answer your question?
Sir, do you lower yourself to answer dumb questions?
I'll take any question you can throw at me. I may not know the answer.
Well, I'm sure you do. Since I've been for years using for a ground where I plug my power cord for my transmitter and everything else through the grounded plug on my back porch, with a ground wire, I might be talking to people not farther away than Colorado and Missouri, mightn't I?
What do you mean with the ground wire?
Because right now I'm not using any ground wire except my AC plug in the back porch.
Oh, okay.
If
Yeah,
I ground that antenna, I might be getting another state or two away, right?
you might get farther along away than that. Yes.
Well, I learned something today, didn't I?
So one of the other things that's happening is you've got a lot of reflected power going back at your radio, and your radio is probably automatically cutting the power out down, even though you have it set at 100 watts. It may turn it down on its own, depending on how new a radio it is, because you don't have a balanced system.
That's amazing.
Your SWRs are probably way off the chart.
Well, I'm using a manual cheapy MFJ antenna tuner. It costs about $100. I bought in 2000, and it works great. But I'm hunting, like we used to say, I'm hunting on the half with a barred dog. So I'm gonna make some improvements as soon as the weather changes.
Yeah, it's going to change this week, but it's not a change where it will get you out and work on antennas, I'm afraid. Don't get
I
cold.
really appreciate your knowledge.
Well, you're welcome. I'm glad to share it. Yes, we hope you learned some more in this class. That's our purpose here. Thanks for learning. Next question. Same type question, different numbers. It wants the ERP relative to a dipole, 200 watt transmitter this time. 4 dB line loss, 3.2 dB duplexer loss, 0.8 dB circulator loss, and a 10 dB antenna gain. So antenna gain starts out at 10 dB. Add up the losses, 4, 3.2, and 0.8. That's a total of 8 dB of loss. So you've given up almost all your antenna gain. You bought this expensive antenna, and then you've got all these losses that subtract from the antenna gain. You end up with a net of plus 2 dB antenna gain. So the factor for 2 dB is 1.58. So you multiply the 200 watts, add 2 dB of net gain from the antenna minus the losses, and you get 317. It's just barely over 50%. If it was 50% extra power in the ERP, the gain factor would be 1.5, but it's 1.58. So you get 317 watts ERP relative to a dipole. See, because the antenna gain is specified as 10 dB relative to a dipole. Okay, you have to watch the antenna gain reference if it's a dipole or if it's isotropic. Because see, what some people can do to sell antennas and make you think you're getting higher gain out of it is make it relative to isotropic. And this would be 12 dB, 12.15 dB relative to an isotropic. And you think you're getting better gain, but you're not. You're only getting 10 dB relative to a dipole. Everybody get that example? Next example. What's the effective isotropic radiated power, EIRP, this time? So you got to watch what it's asking. Of a repeater, 200 watt transmitter. Okay. Losses, 2 dB loss, 2.8 duplexer, 1.2 circulator loss, and a 7 dBi antenna gain. So here the antenna gain is given to us as relative to isotropic. So what do we do with this? To calculate the ERP, it's antenna gain plus 7 relative to isotropic. Add up the losses, 2, 2.8, 1.2, total is 6. So that takes off nearly all the antenna gain. You end up with plus 1 dB out of the antenna over the transmit power. So the transmitter's 200 watts and 1 dB over that gives you 252 effective isotropic radiated power, because this question is relative to isotropic. So the answer here is 252 watts, just barely over the 200 watt transmitter. Everybody follow that? It's the same calculation to find ERP every time. You take antenna gain, subtract off the losses, figure out what the net gain is, and it's transmit power plus the net gain. It could come out to be a loss. So your ERP is less than the transmitter output power. You're eating up all your transmitter power and the losses of all the components. But that's how you figure it. More about isotropic antennas. Isotropic antennas are a very important concept in antenna design. It radiates equally in all directions. And on page 220 and 221, Gordon discusses the isotropic radiator. I haven't copied that, and you can read that later. But right now we're going to be on page 222. From the top, from the side, from the bottom, the antenna pattern for an isotropic radiator is unity in any direction. It doesn't have a pattern. But what we're going to do is to use a Yagi antenna. You see in this diagram down here, sort of the lower left-hand corner, these cross lines, those are elements of a Yagi antenna. What I'm going to do is to use those elements to shape the antenna pattern from an isotropic equal radiation in all directions into a main lobe. That's this big lobe coming out the side off the front of the Yagi antenna. Now it has a little bitty lobe going the other direction off the back end. So that would form the front to back ratio. How big is the front relative to the back? Because with the Yagi antenna, you expect lots of gain off the front, and you want a good front to back ratio so that you can set the backside against interference and not pick up the interference power, but you want to pick up all the power your Yagi's pointed at. And there are side lobes on Yagi antennas. That's these other little lobes coming out the sides. Every antenna has main lobe, back lobe, side lobes. That's the azimuth antenna pattern. The elevation antenna pattern has a main lobe you'd want to be almost horizontal. The closer to the ground level that it comes out, the better. And then here's the back lobe coming out of it. And then we got lobes pointed up into the sky that don't do anything toward getting our main lobe power going around the earth and propagating through the ionosphere. So this is an elevation pattern where you've got half a circle of pattern, and the azimuth pattern is looking down from the top. Oh, the elevation pattern is from the sides, so you see how the power, I call it squirts off, but the main lobe sends the antenna power, and the unofficial engineering term is squirts. The antenna squirts power in different directions. Elevations from the side, azimuth is from the top. I'll use main lobes instead of squirts, but that's what it does. I mean, when you water your plants in your flower bed and you put your finger over the end of the water hose, depending on how you hold your finger over the end of the water hose, it makes a different pattern. You can make it spray, you can make it direct in a stream. Same thing as the antenna. The antenna hardware that you're using mashes or directs the radiated power in a specific pattern that you want. A dipole has broadside to it. Those quarter wave verticals we were looking at, you can make it go linearly off the axis of the two quarter wave verticals. You make it go broadside, depending on how you phase the feed to it. You can make it go cardioid, where the null in one direction and it's nearly omnidirectional all the rest of the way around it, just by the spacing and how you feed those. But the whole point of an antenna is to make the radiated power go in the same direction. Yagi antenna, you want a big front main lobe and a small back lobe and small side lobes. And you can design your own Yagi antenna. We'll talk about that here in a minute. Let's see what else is on here we need to talk about. Oh, yeah, a very important concept. So once you take this isotropic antenna that's radiating a certain amount of power and you squish the RF radiation from it into these patterns down here that the Yagi antenna gives you, it's all the same power. If you added up all the power going off in every direction from this Yagi antenna, it's the same power as what was radiated from the isotropic antenna. The only thing you've done is shape it to where you want it to go. You squish it, you squirt it, you make the power go in specific directions. But if you added up all the power that's leaving this antenna, it's the same power as what left this isotropic antenna. Now, the thing you might have is losses in the antenna, which you have to subtract off. But you can account for that loss because now you know what it is. You know it's antenna loss. And you add up the antenna loss, you add up all the power that's radiated, and that's the same power as you put into that isotropic unidirectional, non-directional radiation pattern. So there's a question about that. How does the total amount of radiation emitted by directional gain antenna compare to the total amount of radiation emitted from a theoretical isotropic antenna, assuming each is driven by the same amount of power? So once you add up all the power and all the little lobes coming off a directional antenna, it's going to be the same total power as what you emitted from the isotropic antenna. Same. It's a long-winded explanation. What is receiving directivity factor? This is the first time I've heard of this. So we'll have to understand what it is. It's the forward gain compared to average gain over the entire hemisphere. Well, let's see. What does average gain over the entire hemisphere means? That means the total power you put into an antenna compared to the forward gain. Where's our picture? So if we add up all the power coming off this Yagi antenna right here in this azimuth antenna pattern, that's the power we put into the antenna. And then the power that's represented by this main lobe that's going off in the main lobe is the forward gain. So that's the useful part of that Yagi antenna pattern. So that means that's called the receiving directivity factor, RDF. So if you have a good RDF, that means you're getting 6 to 8 or 10 dB gain in the forward direction compared to the average gain over the entire hemisphere, which equates to isotropically radiated electromagnetic energy. So you're really comparing the gain that you accomplished in shaping that antenna pattern to the isotropic radiation. And that becomes your RDF. How much gain does an antenna have compared to a half wavelength dipole when it has 6 dB gain over an isotropic? 6 dB gain over an isotropic. And then it says, how much gain does an antenna have compared to a dipole? Antenna has, it wants to know how much gain does an antenna have compared to a dipole when it's 6 dB over an isotropic. And it's answer A, 3.85. The reason is the dipole has 2.15 dB gain over the isotropic. So you have to subtract the 2.15 from the 6, that makes 3.85. You see how that works? No? Let me try it from another direction.
So a dBi is 2.15 and a dB is 6.0, right?
No, not quite. A certain antenna has 6 dB gain over the isotropic. Let's start with that. Let me erase all this. We'll start over. An antenna has 6 dB gain over an isotropic antenna. Okay. The half-wave dipole has 2.15 over an isotropic. You remember that?
Yes.
Okay. So that means that the dipole, this antenna we're talking about has 6 dB over isotropic. A dipole has, this would be a good place for a picture, but I didn't make one. A dipole has 2.15 dB gain over the isotropic. This antenna has 6 over it. So how much gain does this antenna have over a dipole? Is what the answer is. This is what the question's asking. And it's 3.85 because this antenna has 3.85 over a dipole and the dipole has 2.15 over an isotropic. So this antenna we're talking about has 6 dB gain over isotropic. It's just in 2 parts, 3.85 over a dipole and 2.15 over the isotropic. Let me see if I can write this out. Okay. Antenna has 6 dB gain over the isotropic. Okay. The dipole has 2.15 gain over isotropic. Isotropic antenna has 0 dB gain, which is defined as unity gain in all directions. Okay, isotropic has 0 dB gain. The dipole has 2.15 dB gain over the isotropic, and this antenna we're asking about has 6 dB over isotropic. So the question is, how much gain does this antenna we're talking about have over the dipole? Well, the dipole has 2.15 over isotropic. Antenna has 6 over isotropic, so it's 6 minus 2.15. And the difference between this antenna we're talking about and a dipole is 3.85. Is that any more clear?
Yeah, that's clear. So, I mean, we really don't care how much a dB is at this point. We just know that we have 6 dB that we're working with because that's what they're telling us.
Yes.
We're in isotropic. So, and we got 2.15 dB. The dipole has over the isotropic. So we're just doing a calculation here.
Yes, that's right. A dB is a relative measure. It's not anything specific.
Correct.
The only things
I just get confused with dB versus dBi. That's always been a hang up of mine.
okay. Well, we'll try and sort that out.
I just say bananas. I just use bananas instead.
Okay, that works. It can be bananas or inside out bananas or whatever flavor you like. Isotropic is defined as 0 dB gain. It's unity gain in all directions. Unity gain means equals 1. Okay.
Gotcha.
It's because the logarithm of 1 is 0. So that's our reference. That's our 0 reference. Isotropic antenna is 0 reference. The dipole has 2.15 over an isotropic. This antenna we're talking about has 6 over the isotropic. So the difference between this antenna and the dipole is the 3.85.
I gotcha. Okay, let's move on.
Okay,
Break, whatever you want to do.
Hey, John, before you
Hello?
move on, you want to take a break? It's halfway.
this question, then we'll take a break.
Okay.
What term describes station output taking into account all gains and losses? What station output that includes all gains and losses? What would that be called? Effective radiated power, ERP.
Well, now that you say ERP, it makes sense.
Okay. That's what ERP means. All the station output, calculating all the gains and all the losses. Transmitter output plus antenna gain minus losses is your ERP. And it can have 2 different references, an isotropic reference or a dipole reference, depending on which way you reference it. But either way, see the gain of a dipole over a isotropic is mathematically defined. That's from mathematics, so you know that's exact. That's not anybody's one personal dipole. That's the pattern of a dipole, and we'll talk about that after the break. You can study this picture and try and figure out what it all means during the break. Let's take a break for how long? 7 minutes? Short break? Because we're halfway done and we'll need an hour and a half to finish.